Hi, I'm Swapno, and today I'm going to talk about a problem that shows up in Isaac Newton's Principia. Okay, so in Principia, Newton showed that if you have an elliptical orbit, okay, with the force center of the force at one of the foci of the ellipse, then the force varies inversely at the square of the distance from the center of the force. Let's say the center of the force is where the sun is at, and when the planet moves in an elliptical orbit, then the force varies inversely as the square, okay, of the distance from between the sun and the planet, right? But Newton in Principia also considered a hypothetical problem, okay? So he assumed that an object is moving in an ellipse, but the center of the force is at the center of the ellipse instead of being at one of the foci, okay? And he asked the question that what would be the force law if this is to happen? He found out, using geometrical argument, that the force should vary as proportional to the distance, okay, from the center to the planet, okay? So now, it's not inverse square law anymore, okay? Now, Newton used geometrical arguments to come to this conclusion. So what we will do today is we'll use, the tools of calculus, the kind of things like differential equations, equation of an ellipse that you see in an ordinary, that in modern calculus textbook. And and show that that's actually true, that for this hypothetical problem it's indeed the case that the force is proportional to the distance between the center and the object. So last time I made a video where I explained how you derive the elliptical trajectory of a planet, okay, starting from Newton's law, okay. So for today's problem, okay, a lot that we covered in that video applies, okay? All right, so what I'll do is that I'll just write down the final expression that we got, okay, from last time's video, okay? And I'll just briefly outline how we got to that result, okay? But if you want the details, please go back to my previous video, all right? So we obtained an expression which looks like this: d2u d theta squared plus u is equal to gm over L squared. All right, where u is 1 over r. U is the distance between the center of the force and the object, okay, that's r, okay? Like, let's say this is the sun, this is the earth, this is the r, okay? And u is just inverse, it's just 1 over r. Okay, so this is what we derived last time, okay? So, and how did we get that? Let me just outline the steps, all right? So we started out by writing F equal to mass times acceleration, that's Newton's law, and on the left side I have minus gm small m capital M over r squared r hat, and on the right side I have m times r hat times something plus theta hat times something. Okay, I use the polar coordinate system, okay? So acceleration can be represented in terms of r hat and theta hat, okay? In polar coordinate you have this is the r, so r hat is directed this way and theta hat is perpendicular to the r hat. Okay, I explained all these in my last video. Okay, so anyway, then you see that on the right side you have a theta hat component, on the left side you don't have a theta hat component, so this thing should be 0, right? So this should be equal to this because both are r hat components. Okay, so if you equate these two expressions, okay, and u is equal to 1 over r after some algebraic manipulation, you get this expression, all right? So you can see that g is actually the constant of, the gravitational constant. M is the mass of the sun, for example. L is a constant that comes by setting out the theta hat component to 0, okay? So anyway, so let me just explain this term a little bit. So you had gm over r squared, okay, by equating these two r hat components, you get gm over r squared on one side, and on the other side you have some expression which involves, the time derivative of r, which you ultimately write in terms of theta, and all right. So you get gm by multiplying both sides by r squared. Okay. Now instead of gm over r squared, instead of an inverse square law, if you had something like a constant times r, and you multiplied by that r squared, you would have gotten what? C times r cubed, right? And the right side would have remained the same, right? Because you're not doing it, okay? Would have remained just what we had in the previous video in case of a planet moving in an elliptical orbit with the sun at the focus, okay? So the right side doesn't change, all right? But the left side for our problem today, okay, when the sun is at the center of the ellipse, you have this, c times r cubed, okay? Which is like c, if you use this, it should be c times 1 over u cubed, okay? So for today's problem, the equation, from the last time should change a little bit. So the equation would look something like, okay, like this, all right? It would be d2u d theta squared plus u is equal to a constant times 1 over u cubed, okay? If our force varies, proportionally to the distance from the center, okay, as Newton, claimed that it should, okay? So we can check this, okay? That's what I'm going to do today, okay? What I'm going to do is that I'm going to take an ellipse, okay? And I'm going to assume that this is the center of the force, not one on the first side, but the center of the ellipse is where the sun is at, let's say, okay? This is the center of the centripetal force, okay? And the object moves in an elliptical orbit, okay? And I calculate the left side for such a trajectory, and I'll show that you actually get a term, okay? If you simplify this, you get a constant divided by 1 over u cubed, okay? When you have a situation like this, that is the center of the force is at the center of the ellipse, okay? All right, so I'll just outline the steps, okay? It's actually very straightforward, okay, the steps. You will need a bunch of trig identities and, it's algebra and trigonometry mostly, but it's fun to see that it actually works out, okay? So let's get started. So we have an ellipse, okay? This is the center, okay? And let's say the equation of this ellipse is x squared over a squared plus y squared over b squared equal to 1. All right, so this is the equation of an ellipse in the Cartesian coordinate system, right? And so you have this is a, this is b, and so on, okay? So if you use a polar coordinate system, okay? So your x is r cosine theta, and your y is r sine theta, right? So you can plug these two in here, right? And if you do that, and isolate r, okay, you can just write r on one side and everything else on the other side, right? So if you do that, you'll get an expression like this: r equal to ab divided by square root of a squared sine squared theta plus b squared cosine squared theta. Okay, so you can write r as a function of theta, all right? So that means, you can define an u, which is just 1 over r very easily, which would be, you can define u, but you will have a very simple, straightforward expression of u as a function of theta, which would be a squared sine squared theta plus b squared cosine squared theta divided by ab, right? You just take the reciprocal of r and you get u, right? So you have u as a function of theta, okay? Right? So that means you can do du d theta, right? You can take the derivative of this with respect to theta, okay? You have to use a bunch of, all these rules of calculus like, chain rule, product rules, and so on, okay? And if you do that, you're going to get this expression, okay? So I'm writing down the final expression because the calculation should be straightforward. You should get, this for du d theta if you have done the calculations correctly. So it should be a squared minus b squared divided by 2a squared b squared times sine 2 theta divided by u. Okay? So sine 2 theta is 2 sine theta cosine theta. Okay? You have to use this trig identity. All right? So let me write down. So, you need this trig identity and you will need another trig identity, okay, in the calculations that will follow, which is cosine 2 theta is 1 minus 2 sine squared theta, okay? All right, so you calculate du d theta and you can do d2u d theta squared, okay? I'm just writing down the expression, the final expression, in case you want to check that it all works out, okay? And I should encourage you to go ahead and do that, okay? Because that's where the fun lies, checking that it actually works out, okay? So what Newton did, okay, using his geometrical methods, okay, can be proven using, the tools from calculus textbook, okay? So you have this d2u d theta squared is 4a to the 4 b to the 4, and then, okay, I need some space, so I'm going to erase what I have here. Okay, so times, you have u cubed in the denominator, and then you have 4a squared, this is 4a squared b squared cosine 2 theta u squared minus a squared minus b squared sine squared 2 theta. Okay, it doesn't look simple, right? It's kind of messy. It's right. I mean, you have doesn't look there is any pattern to it or whatever. But you have an u cubed in the denominator, and you have this in the numerator. Okay, all right. So the interesting thing is that if you just add these two, remember we are calculating d2u d theta squared plus u, right? We're trying that is what you have on the left side, right? And we're trying to see if this is equal to a constant divided by 1 over u cubed, right? So I have d2u d theta squared, and I have my u, which is just, I just erased it, it's just 1 over r, okay? So if you add the two, if you do d2u d theta squared plus u, okay, then from all this mess, you get a very simple expression. I was actually surprised when I actually went through these steps, and I was like, I couldn't believe that it was such a simple expression, okay? But it does come out as a very simple expression, which is 1 divided by a squared b squared divided by 1 over e cubed. Okay, so you have d2u d theta squared, which has all these complicated terms, and you have du d theta, which also has theta and so on. But if you just add these two and do some algebra and use these trig identities, okay, you have to use these two, okay, then you get a simple expression like that, okay? And that is exactly what Newton, predicted, that, on the right side, you have 1 over e cubed, and that means the force varies proportionally to the distance, okay, from the center, okay? So this term, the significance of this term is that the force, let me just write it down here, force is constant times the distance, okay? See how different it is from the gravitational force, right? For gravitational force, it's what? It's k times 1 over r squared, right? It falls off inversely as the square of the distance. But if instead of the sun being at the center and sun being at the focus, okay, it was at the center of the ellipse and the planet moved in an elliptical orbit, then your force law would have been this, k times r, proportional to the distance instead of falling off inversely as the distance. Clearly this is, unphysical, right? Because force cannot increase with distance. I mean, common sense says that, it should, the farther you're away from the sun, the smaller would be the force, right? But it's fun to see that this hypothetical situation, you can also find a force law for this hypothetical situation. Okay, thank you for watching the video. I hope you enjoyed it.